Also want to thank the organization. I'm going to talk about an ab initio comparison of the magnetic properties of the M-type and the W-type strontium hexaferrite. Yeah. So the reason to compare both materials is to look for rare air-free permanent magnets. So we can measure the efficiency of permanent magnets using the energy product, and the best one are based on rare earths. The problem with rare earths is that they are critical raw materials, they have a huge environmental impact, and they are quite expensive. So the idea is to look for alternatives, and among the alternatives we have the ferrites, and our main goal is to improve the properties of the ferrites. So in the family of ferrites, the most important one for permanent magnets application are the hexagonal ferrites, especially the M-type hexaferrite that it's already used in the industry. And we're going to compare this material with another material of the same family, which is the W-type hexaferrite. It has been shown experimentally that the W-type hexaferrite can improve some of the magnetic properties of the M-type hexaferrite. So in order to compare both materials, we are going to use DFT to compare electronic and magnetic properties. We're going to use this FAIR method to compare the enthalpy of formation and stability. And then we are going to use first state energy mapping plus atomistic simulation to compare the exchange interaction and the critical temperature. So both materials are made with these two blocks. These are an S block, and the difference is in the stacking sequence. So for the M-type hexaferrite, we have an RS stacking, while for the W-type hexaferrite, we have an RSS stacking. And because the stacking is different, there are two key differences. The first one is that for the W-type hexaferrite, we have a new crystallographic position for iron, which is this 6G octahedral position, which is the bounding position between two S blocks. And for the W-type hexaferrite, also we have iron 2 plus and 3 plus, while for the M-type hexaferrite, we only have iron 3 plus. So before comparing both material, I just want to mention that the properties depends on the Hubbard-U parameter. So we calculate the properties for different U values. So first, we study the stability. So in order to do that, we calculate the enthalpy of formation and the stability region. The stability region basically gives us the region where the most stable compound, where the compound is going to be the most stable one compared to the competitive phases. So here is the stability region for the W-type hexaferrite, and here is the projection. And when we add the competitive phases, we can see how the stability region gets smaller and smaller. So in this case, for the W-type hexaferrite, the competitive phases are going to be the EMA-type, magnet-type, N-type, X-type, and strontium oxide. And we can do the same for the M-type hexaferrite. And what we see is that the stability region is going to be smaller for the W-type hexaferrite. So that means that in principle, it's going to be more complicated to synthesize the W-type hexaferrite. So for example, if we fix the temperature, in order to synthesize the W-type hexaferrite, we're going to need low oxygen pressure conditions. Then we can compare electronic and magnetic properties. So the R and S block have similar magnetic properties. Both blocks have 4 spin in the up direction and 2 spin in the down direction. So each block has a net total moment of 2 irons. But the difference is that, again, for the W-type hexaferrite, we have this iron 2 plus, and the iron 2 plus has a smaller spin moment. So when we calculate the magnetization is going to be slightly lower for the W-type hexaferrite compared to the M-type. This iron 2 plus is located in the position that I mentioned earlier, this 6G octahedral position. And another consequence is that the W-type hexaferrite is going to be a half metal due to this iron 2 plus that again is located in this position, while the M-type hexaferrite is going to be an insulating material. Then we can calculate the magnetocrystalline anisotropy. So both materials, M type and W type, have uniaxial anisotropy along the z-axis, so we can calculate the anisotropy as the difference in energy with a spin configuration in plane and perpendicular to the plane. And what we found is that the anisotropy is going to be higher for the M-type hexaferrite. So there are two reasons for that. The first one is that the radio of air block is higher for the M-type hexaferrite. And the most important contribution to anisotropy is coming for this R block. The reason is that in order to create this R block, we are replacing one strontium by oxygen, which is breaking the symmetry and increasing the anisotropy. And another reason is that if we calculate the contribution of anisotropy of each of the ions, what we found is again this new crystallographic position is giving a negative contribution to the anisotropy, which also decreased the anisotropy for the W-type hexaferrite. Then we calculate the exchange interaction. So in this figure, I have the exchange interaction for the different ions for the W-type hexaferrite as a function of the distance. The most important interaction are the closest one. And if we represent this interaction with the oxygen angle, they follow nicely this rule over here. So that means that these interactions are mediated by super exchange, and almost all the interactions are antiferromagnetic, with the exception of this interaction. And this interaction corresponds to the ions located again in this new crystallographic position, this 6G octahedral position. And what happens here is that here we have iron 2 plus and 3 plus. So we have a ferromagnetic coupling due to the double exchange interaction. We can calculate the Curie temperature using the vampire code. And what we found is that the Curie temperature is going to be higher for the M-type hexaferrite. And if we compare the most important interactions, the most important exchange interaction between the double type and the M-type hexaferrite, the reason is again this crystallographic position, because the interaction is going to be lower between this crystallographic position and the another irons. So based on DFT, the best material for permanent magnets application is the M-type hexaferrite, but it's important to remember that DFT is only valid at 0 Kelvin, so this conclusion in principle is only valid at low temperatures. If we compare this value with values at room temperatures, what we found is that actually, based on experimental values, at room temperature, the best material is the W-type hexaferrite. And the reason is that the anisotropy, so this data here is experimental data, and the anisotropy field of the W-type hexaferrite increase with temperature, and also the magnetization decrease slowly with temperature. So at higher temperatures, the best material is the W-type hexaferrite, and this behavior is also related to the presence of iron 2 plus. Finally, I just want to discuss two ways of increasing the magnetic properties. The first one using hydrostatic pressure, and the second one using chemical substitution. So in the case of hydrostatic pressure, the idea is quite simple. If we compress the system, it's going to increase the anisotropy. So for example, for the case of the W-type hexaferrite, if we compress the system, we can reach similar values to the M-type hexaferrite. And for the M-type hexaferrite, we have the same. If we compress the system, we can increase also the anisotropy. For the case of chemical substitution, we studied the case that when we replace one iron by another ion for the double type hexaferrite, and what we found is that the ions tend to go to this position again, this new crystallographic position, and the effect is that there is not big changes in anisotropy for the different ions, while the magnetization decreased for the most of the case, with the exception of manganese. The reason for the decrease of the magnetization is that at the end what we are doing is we are replacing iron with another ion with a smaller spin moment. So this is in good agreement with experimental evidence, but what is really interesting is that if we increase the concentration of zinc, for example, to zinc equal 2, the position where the zinc is going is not longer going to be this 6-deoctahedral position, but it's going to be this 4e tetrahedral position. And in this case, we are actually improving the magnetization. So maybe changing the concentration of these ions is a way to improve the magnetic properties of the W-type hexaferrite. So as a conclusion, we compared the double type and M-type hexaferrite. We found that the M-type hexaferrite for permanent magnet application is better at low temperatures, while the W-type hexaferrite is better at higher temperatures. The M-type hexaferrite is an insulating material, while the double-type hexaferrite is a half metal. One of the biggest problems of the W-type hexaferrite is that it's more complicated to synthesize compared to the M-type hexaferrite. We can increase the properties using hydrostatic compression and using chemical substitution with specific ion and specific concentrations. Also, despite that DFT is limited to 0 Kelvin, it's still useful to study the physics behind the structures. For example, thanks to DFT, we can study that this iron 2 plus plays a crucial role on the magnetic properties of the W-type hexaferrite. I just want to thank Beethoven European project, and I just want to mention that this work is part of the European project Beethoven. Thank you very much.
Well, thank you for the talk. There are any questions? I can see anything on the chat. Okay, so I can start. Can you go back to slide 10, please?
This one?
Yeah, here in this graphic on the left, you have some red dots and some blue dots. What is this for? What?
I know it's just to it's just to clarify that these points are the closest one, and here I only represented the closest points.
Okay,
Yeah.
so they are all the same for the same material and
Yeah, it's for the same material. Yeah, these points only belongs to the W-type hexaferrite.
okay. And can you maybe go to slide 14?
14.
Yeah, you mentioned that it kind of decrease the magnetization for all materials, except for the manganese. Do you have any reason, an idea why it would happen, why manganese is different?
So for the rest of so when I'm replacing the iron by another ion, for zinc, nickel, magnesium, and cobalt, what I'm doing, I'm decreasing the spin moment.
Mm,
So in the case of manganese, manganese has higher spin moment. So that's the reason that it's increasing the magnetization here for that specific case.
okay.